Well, hello everyone. I thought I would step in here and give you a little talk about the First Isomorphism Theorem and show you some applications of it. It really is a fundamental tool and a very important concept in group theory. And in fact, there's versions of this theorem for ring theory as well. But for right now, we're going to focus on group theoretic applications of the First Isomorphism Theorem. I've stated my version of this theorem here on the board. You have to have a homomorphism from a group G to a group H. And let's just call the kernel of that homomorphism K. Just with that setup, right, so you can really do this with any homomorphism, if you mod out by the kernel, form a quotient group, it will always be isomorphic to the image of the homomorphism. Okay? In particular, if the homomorphism is onto, then this f of g here, this image of the homomorphism, if in the onto case, this would just be h, right? Also, don't forget that the kernel of a homomorphism is always a normal subgroup of G. That's why I know that it's safe to form this quotient group G mod K. Okay, so it's a little bit of the background. On the board here is a quick application. There is no surjective homomorphism possible from Z68 to Z12. And the proof is here in the blue writing. It's very short. You just approach it by way of contradiction. And imagine that there was such a homomorphism. When you apply the First Isomorphism Theorem to this function f, you get that Z68 modulo the kernel is isomorphic to the image of the function, which for a surjection would be the whole Z12, right? And then you just compare sizes, right? The quotient group on the left has a size that's 68 divided by the size of the kernel, and the size on the right is just 12. And so the kernel, the size of the kernel would not be an integer in that case. So the 68 and the 12 do not form an integer as a fraction. And so that's your contradiction, because the size of the kernel, of course, has to be an integer. And you notice that there's nothing special about the 68 and the 12 other than the fact that the 12 does not divide into the 68. Right? That's all that you need in order to make that case. Let me show you a few more applications of this First Isomorphism Theorem. It turns out we can do something very similar with injections as well. So I'm going to give you an example of that nature. So there is no injective, in other words, one-to-one homomorphism there we go. There is no injective homomorphism F, let's say from Z15 to Z20. So we're taking a set of size 15 and we're trying to create a mapping or a function into a set of size 20. It would be possible to make a one-to-one map like that, but you're not going to get a one-to-one homomorphism like that. In other words, you're not going to create a function that respects the group operations, in this case addition, from Z15 to Z20. Okay? To prove this one, it's almost the same kind of idea as what we did on the first application. I do just want to make a note of something here, and this is something you may already have realized. It's actually stated as a theorem in the book, and what this says is just that basically F is injective, this is just a general fact, if and only if the kernel is trivial. Okay, so this is the same kind of theorem that you would have in linear algebra, right? So the kernel of an injective homomorphism is always trivial. So let's just go ahead and, if you want, you can take a look at the proof of that. It's theorem 8.17 in the book. I'm not going to prove it here in this little talk. I'd rather get back to proving my example here, or my application, I should say. there is no injective homomorphism from Z15 to Z20. Let's approach it exactly in a similar manner by way of contradiction, right? If such F exists, okay, then let's just see what the First Isomorphism Theorem tells us. Okay, so by the First Isomorphism Theorem, in that case, well, what would we have? We would have Z15 modulo the kernel, but of course the kernel for an injective homomorphism is just E, right? So that's G mod K right there, is isomorphic to whatever F of Z15 is. Okay, so the image of the function. All right, well, is there a contradiction here? Well, remember that the image of a homomorphism is always a subgroup of the codomain, right? So in other words, this F of G right here, right, this is actually always going to be a subgroup of H, the image of a homomorphism. So what we can do is we can write that this is a subgroup of Z20. Well, that means that by Lagrange's theorem, so I'm actually going to use Lagrange's theorem for this, the most important theorem in finite group theory, right? By Lagrange's theorem, the size of the image of our function has to divide the size of Z20, and the size of Z20 is just 20. But look at the image of our homomorphism. It's isomorphic to something that has size 15, right? So the size of the image of the function, this makes sense. If you have a one-to-one function, you're going to have, here are 15 inputs, you're going to have 15 different outputs, right, for a one-to-one function. So what you're saying now is that 15 divides 20, and this is, again, a contradiction. So it's very similar to showing that there's no surjective homomorphism over here. We do use Lagrange's theorem briefly to say that, look, the image of our homomorphism is a subgroup of the codomain H, which is Z20, and therefore the sizes have to divide into one another. Okay? So there's another little contradiction. Okay, so we can prove that there do not exist injective or surjective homomorphisms in certain cases. In this example, it doesn't have to be Z15 and Z20, does it? Right? It can just be any groups of size 15 and 20 right here. Yeah? Because never are we really using the detailed nature of the group. We just really, the only thing we're really using in either one of these applications that we just did is the size of the groups that are involved. That's really all that comes into play. So we could change these groups to non-abelian groups or non-cyclic groups. The cyclicity of the groups that I've been using in these examples is not really of fundamental importance to why these things are working. Okay, let me show you a few more examples or applications. There is a homework problem in our book that discusses something called the Second Isomorphism Theorem. I think I'm going to skip over that and instead talk to you a little bit about the Third Isomorphism Theorem, which is a really nice one. It's actually also in our book. Let me see if I can find the statement of it here. I misplaced my notes. Here it is. So let's go and write down application number 3 of this First Isomorphism Theorem. Okay? So we'll go ahead and kind of start fresh here. Okay, so here's what it says. Let K and N be normal subgroups of G okay, with the following relationship. Let's suppose that N is a normal subgroup of K, which is a normal subgroup of G. All right? Then, as it turns out, K mod N is a normal subgroup of G mod n. Okay, so we can form these quotients, right? Because everything is normal inside of everything else, right? And because K mod n is normal in G mod n, we can actually form a quotient group out of that relationship. So G mod n, I can mod out by the normal subgroup K mod n. This is going to be another group, and it turns out that it's isomorphic to G mod K. All right, so this is commonly known as the third isomorphism theorem. So again, the second isomorphism theorem is something in the exercises of our book. So we have the first isomorphism theorem, and now this is the third one. Okay, and the nice thing here is that if we want to prove this, we can use that first isomorphism theorem. So let me just do that for you right here. Let's write down a proof of this third isomorphism theorem. We're going to prove this using this. So the way I'm going to think about this is I'm going to create a homomorphism from the top group, right? From the G mod n that goes hopefully onto G mod K, such that the kernel of that function is exactly K mod n. Okay? Does that make sense? So just looking at the relationship of the pieces. The domain is on top, the kernel is on the bottom, and the image of the function is on the right-hand side. So the domain of this function I'm about to write down is going to be G mod n. Hopefully the kernel of that function I'm about to write down will be K mod n. And hopefully this will be the image of the function, G mod K. Let's try it. So I'm going to define, the whole trick with using the first isomorphism theorem is that we have to actually define the function. So I'm going to define a function that goes from G mod n over to G mod K via, well, I have to do what? I have to input a coset here, and a coset here is going to look like something like NA, right? I'm going to write it as a multiplicative right coset, okay? So I'm plugging in a coset from G mod n, and I'm required to spit out a coset from G mod K, right? And what I'm going to use for that is just the natural thing to use is going to be some coset of the form K something. I may as well just use the same A right here. By the way, I need to be very clear about one thing really quickly. The K that you see in this third isomorphism theorem is not the kernel of anything. Okay, I'm a little bit abusing notation because the first isomorphism theorem, we're talking about this kernel K that goes with this homomorphism. That is not related at all to the K that you see here in this third isomorphism theorem. What I have here is just two normal subgroups in a chain inside of G. And that's all that I really need to know. Okay, so this is the function I'm going to define. Okay, and what I'm going to do is I'm going to try to prove all of the parts that I need in order to apply this first isomorphism theorem. Before I even check that my F is a homomorphism, I'm going to check that F is well defined. You notice once again in this example, right, what we have is a domain that consists of cosets. And we need to make sure that if we have two different ways of writing the same coset, let's suppose that NA is equal to NB, I need to make sure that F of NA would still agree with F of NB, right? So let's see if I can do that. Let's assume that NA is equal to NB. Then you may remember that we can move the A inverse over to the other side and write an element relationship like that. BA inverse is an element of N. This comes from our earlier material when we were first looking at equality of cosets. Okay. However, notice that N is inside of K. Right? So N is actually inside of K right here. And that means that BA inverse is actually inside of K. And thus, Ka will in fact be equal to Kb, right? And that means that therefore f of Na does in fact agree with f of Nb. Okay, so this is a very quick little verification that my function is well defined. Once it's well defined, now I can go forward and check some other things about this function f that we have created here. Okay, so again, I've created a function that goes from the top of this left side over to the right side, and I'm going to check that hopefully its kernel is exactly k mod n, and hopefully its image is exactly g mod k. We're going to check all of that. Let me start with just the homomorphism part. So let's check f is a homomorphism. This part isn't really too bad. You know, you just have to take two cosets, right? So we could just say, you know, let NA and NB be elements of G mod n. And we're just going to look at, you know, f of, what is it, NA times NB right here. Okay? And I can actually just multiply those cosets together in the usual manner. I'll get f of NAB. And now I have a single coset that I can just apply my formula to. It's supposed to be KAB. But then that can be broken up as KA, KB. Oops, let me write that again. KA times KB. And that is just f of NA times f of NB. So this is just straightforward to verify that the function that I defined is actually a homomorphism. I hope that you can read all of this stuff. I'm trying to save my space just a little bit here. Okay, so we have a homomorphism. Let's figure out if it's onto or not. I'm claiming that f is onto. So let's just say a quick word about that. To show that f is onto, I have to grab an arbitrary element of G mod k. Right, so I'm just going to grab any coset I want. I'll just call it kx that's in the codomain, right? And then my job is to figure out a coset in G mod n that would get mapped to it. Okay, but there's nothing to this, is there? Right? If I take kx as my coset, well, then I can just note that f would send what? Nx to kx, right? Just put a little check there. That's all there is to that. So this is very easy to see that this is an onto homomorphism in this case. And then the last part of it that we need to verify is the kernel. Okay, so we need to verify that the kernel of this homomorphism is actually k mod n. Okay, so we're going to do that. We're going to check that the kernel of f is equal to k mod n. I need to check this part. Okay? I'm a little short on space here. I'm going to erase the check that f is well defined and a homomorphism, if that's all right. We've already done that part. If you need to pause or rewind or copy something again more carefully, of course, you can do that on a video, which is kind of nice. So I'll let you do that if you need to. I'm going to check this, this kernel thing right here. So I'm going to check that the kernel of this function that I just defined right here, here's my function, that it's actually equal to k mod n. Okay? And I think that this is an equality, and when you have an equality of sets, you can, of course, prove subsets both ways if you want to. I'm going to try and argue the whole thing kind of in one breath. I'm going to do sort of a series of biconditionals. So to do this, what I'm going to do is I'm going to say, well, NA is an element of the kernel of f, and I'm going to kind of create a series of equivalences here. And hopefully at the end of the day, I'm going to have NA living in k mod n. All right, so let's see if we can get to that. So if NA is in the kernel of F, what does that mean? Well, that means if you apply F to NA, you're supposed to get the identity element of the codomain. Of all of these cosets, of course, the identity coset is just K itself, or KE, if you like. Okay? But now if I just plug in what F of NA is, we see that it is Ka. So we're saying that Ka equals K. And again, from one of our early little exercises about cosets, this is just equivalent to saying that A is an element of K, right? So you might recall that. And if A is an element of K, then when I'm looking at NA, if I look at that whole coset, right, that is now actually in K mod N. Right? So remember, what does K mod N look like? These are just cosets of N with representatives from K, and that's exactly what we have here. Okay? So because of this little chain of statements, we've verified that the kernel of F right here is the same as K mod N. Okay? Once you've checked all of these things, you check that F is well defined, that it's a homomorphism, that it's onto, and that the kernel is what it's supposed to be. Now, you just simply finish by saying, look, right, by the first isomorphism theorem, the result follows. So that at this point, you've got all the pieces, all the little verifications that you had to do, and you don't really have to do any more heavy lifting. You just simply have to write down that the result is true now, okay, using that first isomorphism theorem to do it. So that's a nice application, I think. I really like that particular problem. You might have noticed I did forget to do something. Technically, I should have checked that K mod N is a normal subgroup of G mod N before I formed this quotient group. Right? Technically, you can't form a quotient group unless the thing you're modding out by is a normal subgroup of K mod N. Maybe you'd like to see me show that real quick. So just a really quick check here that K mod N is actually a normal subgroup of G mod N. You get so carried away by the coolness of this isomorphism, where you're basically canceling the ends, that you forget that you really have to check this first, right? I should have probably done that. So you have to check that you have a subgroup and that you have a closure under conjugation, right? So K mod N, right, the closure under the operation, you would just simply, I'm going to be a little sketch, just a little sketch of this, right? You would take what? You would take a couple of elements out of K mod N. So they might look like NK1 and NK2. And this is very straightforward because if you now just multiply them together, right? If you just multiply these cosets together in the usual manner, you realize that since K1, K2 is a product inside of K, which is already a subgroup, that therefore this is already closed under multiplication, right? And then similarly, the closure under inverses is going to follow pretty easily. So if we just look, I'm just going to take the same NK1 again. The inverse of that coset, as we know, that's just going to be the coset NK1 inverse. Okay, and this is, again, because K is closed under inverses, that means that K mod N is now closed under inverses. Okay, and then under conjugation, right, what are we going to be doing for that? Well, we're going to be taking something like, NG inverse times NK times ng, right? This is what a conjugation expression would look like. And you just simplify this thing down. It's just n of g inverse kg. But k is a normal subgroup of g, right? So it is closed under conjugation itself. So this expression here is inside of k. And so you just have something that is inside of k mod n again. Okay? So that's pretty easy to just verify those quick facts. So I should have checked this first. Okay, I apologize for that. I should check first that I have a normal subgroup of something before I mod out by it, which is what we're doing in the statement of the theorem here. Okay? But that's the verification for that part. Okay. The third isomorphism theorem will not get used as often as the first one. This first isomorphism theorem is really the one that we find so many beautiful applications of, and that you're going to hopefully get a lot of practice with. Let me see. Maybe I'm going to maybe do one more example of this, and then we'll call it good for now. Let me find what I want to do here. Yeah, let me just do one more application, I guess. This would be application number 4 in my list. Let's suppose that we have a direct product of groups. So suppose G1 and G2 are groups. Then G1 cross G2, we can mod out by G1 cross the identity of G2. And I claim that that's just isomorphic to G2. Okay. There's going to be some problems in the book for like homework exercises that generalize this result. So maybe just showing you this will kind of give you a feeling for what those results are going to look like. So let me just write a sketch of the proof here. I'm not going to do the whole entire thing. I'm just going to take like 1 minute to set this one up, okay? So again, to use the first isomorphism theorem, I'm going to define a function from the numerator of the left side, which is G1 cross G2, to the right side, and hopefully the kernel is going to be G1 cross E, okay? And the way that you would do this, well, you're going to take an element, let's say G1 comma G2 inside of the cross product group here. What is F going to do to that element? Well, it needs to give me an element out of G2. And the natural thing to do is to just take this G2 and just put it here as your output. Okay? And it's going to be easy to check, I won't do it right now, that F is a homomorphism. Okay? That F is onto, it's very clear that F is onto, and that the kernel of F is just, well, which pairs end up sending to E here? Well, they're just going to be pairs that have anything from the group G1, comma, E, and that's exactly G1 cross E. Okay. So these things are all very easy to check, and therefore this isomorphism follows immediately. Okay? And you can modify this example, as I said, and make it a little more general than the result I've stated here. Okay, these are some great examples of using the first isomorphism theorem. I hope most of this has made good sense. Feel free to ask me questions, send me comments or feedback. I'll be happy to do anything I can to try to help make this more clear. I'm a big fan of this first isomorphism theorem and its many applications. Thanks for watching, guys. I'll see you again soon.